Fun fact: take any 3 points, connect them with lines to form a triangle, build equilateral triangles off of each side, then find the centers of those equilateral triangles. When you connect those centers, you'll get another equilateral triangle, no matter which 3 points you start with. This is Napoleon's theorem, named after the Napoleon Bonaparte, who, aside from being a military commander and emperor of France, was also an amateur mathematician, with special interest in geometry. Although, it's not at all clear whether he really had anything to do with this particular theorem. Now, I was asked by a viewer whether Napoleon's theorem could be proved using vector sums, like the proof in my video on von Abel's theorem. These theorems are similar, so I figured, why not? Challenge accepted. The first thing to do is decide how to prove that a triangle is equilateral. One way is to show that all 3 sides have the same length. But it is also sufficient to show that 2 of the sides are equal and that the angle between them is 60 degrees. This works well for a vector proof, since a vector encodes both a length and a direction. So for this proof, I'll construct vectors along each of these sides, like this, and then rotate one by 60 degrees counterclockwise. If this makes 2 vectors that sum to 0, then that means they are of equal length and direction, and were therefore part of an equilateral triangle to start with. Next, we'll need to look at what it means to be the center of an equilateral triangle. Triangles have many centers, and for a random triangle, they're all different. The 4 most commonly used are the circumcenter, the incenter, the orthocenter, and the centroid. Fortunately, for an equilateral triangle, these are all the same point. So we can choose whichever definition is the easiest to work with, which is the centroid. If we put the triangle in a coordinate system, the centroid can be found simply by averaging the 3 x coordinates and the 3 y coordinates of the vertices. In vector terms, that means adding the 3 vectors from the origin to the vertices and dividing the result by 3. Or, if we choose one of the vertices to be the origin, then one of the vectors disappears, and the other 2 coincide with the sides of the triangle. Again, we can add the vectors and divide by 3 to find the center. Or, better yet, divide those 2 vectors by 3 before adding them together. And that is how we will define the vectors that we'll use for this proof. Consider vectors A, B, and C, which take you from each of the vertices to a point 1/3 of the way along the corresponding side. Note that these vectors added together form a closed loop, which means they sum to 0. Rotating the vector A 60 degrees counterclockwise creates a vector that I'll call A'. As we saw moments ago, adding that to A gets you to the center of the triangle built on that side. Rotating it by another 60 degrees gives us A', and that can bring us to the same center from the other direction. But we'll want to continue in the same direction, so we'll be using negative A'. Rotating that by 60 degrees counterclockwise gives us negative A', which, it's not hard to see, is the same as A. Using this system of vectors and rotations, we can express the vector between the first pair of centers as negative A', plus A plus B plus B', and the vector for the second pair as negative B', plus B plus C plus C'. Following the recipe we discussed earlier, we'll rotate the first one 60 degrees counterclockwise, which adds a prime to each of the constituent vectors. Notice that this one is now negative A', which is the same as A. So, if we can show that these 2 vector sums added together will always result in 0, that would prove they started as 2 sides of an equilateral triangle. Ready? Ta-da! The sum of all these vectors is nothing more than 0 plus 0 plus 0. QED, and how cool is that? Before you go, I should point out that Napoleon's and Van Obel's theorems are both special cases of a theorem that works for polygons with any number of sides, called the Petter-Douglas-Neumann theorem. This is a marvelous theorem that lends itself to some really nice animations. And maybe someday I'll figure out how to explain its proof clearly enough for another video.